Good morning, Professor. It's a great honor for us to receive you and to listen to your presentation. Before I give you the floor, I present rapidly Professor Mekhilef. Professor Saad Mekhilef is a IEEE and EAT Fellow. He is a distinguished professor at the School of Science, Computing and Engineering Technologies in Swinburne University of Technology, Melbourne, Australia. He is an honorary professor at the Department of Electrical Engineering at University of Malaya and a distinguished visiting professor at the Institute of Sustainable Energy, University Tenaga Nasional, Malaysia. He authors and co-authors more than 600 publications in academic journals and proceedings, 5 books with more than 7,000 citations, and more than 85 PhD students who graduated under his supervision. He serves as an editorial board member for many top journals, such as IEEE Transaction and Power Electronics, IEEE Opening Journal in Industry of Industrial Electronics, EIT Renewable Power in Energy Power Generation, IPRIM, Journal of Power Electronics, and International Journal of Circuit Theory and Application. Professor Mekhilef has been listed by Thomson Reuters Climate Analytics as one of the world's highly cited in the top 1% in engineering researcher. He also listed in the world top 200% of science by Stanford University, USA. He is actively involved in industrial consultancy for major corporations in the power electronics and renewable energy projects. His research interests include power conversion techniques, control of power converters, maximum power shrinking, and renewable energy and energy efficiency. Professor, you have the floor.
Thank you very much. Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. And very good morning. It's always a pleasure to be here in Setif. Shukran, Prof. Karim. Prof. Karim was my teacher. He was teaching me. He was my lecturer. I'm very proud. I'm his student. So what I have achieved is because of his teaching. And all the lecturers at University of Setif. What we have achieved is all due to our teachers and all the work they have done to us. And the moment he sent me an email and asked me to come and give a lecture, even it's not in my program, but I say yes. And I make my time to come and inshallah to share with you what I have learned, And it's always to see good friends, here. And so what I'm going to share with you this morning is about the role of power electronics. Power electronics, it's a very dynamic topic which is evolving and emerging, and lots of innovations have been done in this area. And how we can achieve this, what we call neutral carbon society, because that's the trend now. The current emissions level is increasing day after day on how we achieve a neutral carbon society. And what I'm going to show you is how we engineers can play a role in this change, or what you call energy transition. So I start with some questions. Is why the climate sustainability is challenged. Climate sustainability is very challenging, very complex, and because it's always comes with challenging compromise that you have to make. For example, the need of energy and the energy emissions. So when we need the energy, we need to burn oil and gas. On the other hand, we will generate carbons and emissions. So human beings is always in a difficult situations on how to sustain, how to meet the needs, but in the other hand, you have to sustain the climate and reduce the emissions. And for the last 100 years, there has a lots of programs and meetings and summits to try to reduce the carbon emissions. And I will show you some of the disasters. We've seen unprecedented disasters everywhere. So what we see this kind of floods happens not only in certain regions, but across the continent, across the world, from Africa to China, to United States, to everywhere. This is not used to be in the last 50, 60 years. We see this kind of situations everywhere. We've seen this 2020, in Pakistan, one of the largest floods. 5 million people have been displaced. 5 million people. We're talking about hundreds of thousands of people died. Never happened before. So this kind of situations, we see this. You see in everywhere. So for example, in the United States, states which never been experiencing floods. Okay? We see this kind of in New Zealand and even in Australia last year. We had the floods which we never had before in the last 100 years. Never before. Before the floods, we had what they call bushfires. I don't know, you heard about it in 2018. We had a lot of bushfires, So we see this in New York, even in New York, So we see this kind of disasters. And also, if we don't see the floods, we see this. Drought. I'm not sure you have been here or not. This is in China, in Yangtze River. Yangtze River, I have been to this place. It's in the center of China, where the largest power hydro in the world, 18 gigawatts. They built this hydropower plant in China to control the floods. Last 2020, what happened to it? Parts of this rivers that supply this large hydro dries out. So we see this kind of natural disasters happening almost everywhere. And if we also see this, wildlife fires. See, this is in the United States, in Arizona, in California, so fires that have never been before. And you can see this, very close to us in Algeria. And even in Algeria happens before. So we see this, France, Portugal, Germany, Greece, Spain, Italy, the whole Europe on fire. This has never happened before in the last 100 years. So what we can see that actually, even in Siberia, one of the coldest place in Earth, we have these kind of fires. So this is an alarming, what I call signals, that we need to do something. We need to act, and to have to act fast. Because if we continue this way, we will reach to a stage, we call it the irreversible state. The irreversible state means whatever you do is too late. You cannot change anymore, whatever you do. So if we want to act, we have to act today, not tomorrow. So that's actually the situation. And in Algeria, last year, I've extracted this, it reaches almost 53, degrees, That never happened before. So we can see this kind of signals and this kind of indicators that shows actually the climate is changing, and is changing very fast, and we need to do some acts. We see also disasters, even snowstorms everywhere. So what's the cause of this? What all the cause of these problems? The cause of this is the emissions that we generate. The CO2 emissions that generated from our energy use and our energy consumption. And I think you all know that the energy consumption per person is increasing. I think increasing, right? I came from a very small village in the northern part of Setif, a small area, I don't know, maybe some of you have been there, It's an area which is the three wilayas, Jijil, Setif, and Mila. I think a place called Walban. That's my first primary school, I did my primary school in that area, very isolated area, Now it's famous of Shua, تحب أنتوا تأكلوا شو تروحوا الولبان, you know, very touristic place. You know, in that place, in that village, the whole village in the 70s, you know, talking about 1974, 1975, you know, almost 50 years ago, there is only one car, the whole village, and that car used for everything, as an ambulance. If someone gets married, you have to bring the bride in it. If someone is urgent, you have to go to that car. You know, one car in the whole village, and that person, very important person, you know. It's more than the chef daira or the lueli, you know. That's very important. He has a car, you know. So everyone needs it. I went to the same place 40 years later, to the same village. What I found, every house, there are 3-4 cars. What does this mean? Yeah, from the economic point of view, maybe people get richer. The economic is good. People are getting well. But from energy perspective, for me, I look from the energy perspective, the consumption per person has increased. Last time, one village, one car. Now, one house, 3 cars. So the energy consumption is increasing. Just imagine, 20 years ago, how many of you have a mobile phone? None. Today. No one without a phone. So that's energy. You need energy to run this phone. How many laptops? So the energy consumption per person is increasing. So when the energy consumption, so there will be emissions, okay? And what you can see, the level of emissions is, you know, it was stable until the last century. You can see there is a big jump, you know? So this actually giving us another warning, you know? This is the history, you know, for the last thousands of years, the level of carbons was below the required. So, and you can see it's an exponential increase of all the last 200 years. The Earth temperature also is increasing, and that's why we have this Paris medical summit. We have the COP18 in Glasgow, and then everywhere trying to limit the Earth temperature. So that's, and this is the impact of this, the Earth temperature. Maybe in Algeria we don't see it, but if you go to some countries, you can see the impact of this. You know, I've been to this Bangladesh, you know. Bangladesh is a very poor country. During the raining season, 25% of the land of Bangladesh goes underwater. 25%. Can you imagine? 25% of Algeria goes underwater. The Pacific Islands, you know, in Australia, between Indonesia and Australia, there is a lot of islands. We call them the Pacific Islands. You know, one of them, maybe I give you an example, Maldives. I don't know how many of you have been to Maldives. Maldives is a very good place for tourists, but very expensive. You know, the highest level from the sea, it's around 5 meters. Means the whole country will disappear actually if the sea level rise, and it's increasing, and this will lead to increase of the sea level rise. Okay, who is the problem? Where the problem come from? It coming from developed countries. They are trying to reduce. You can see the matured economies, they have already trying to reduce, but the emerging, like India and China, is contributing a lot to these emissions. Currently, now. But in the history, is the other way. History, you can see 23 rich countries contributed more than 50% of the carbons. So we're talking about the United States, Europe, Japan, Australia, and so on. And the other 50% is contributed by another 150 countries. So this is history. Who is responsible for this? Who is responsible is all the developed countries. Okay, so that's in terms of history. So how we address this problem? We have the problem. So how we are going to address it? How we are going to solve this? Because there is no point of saying this is United States, this is Japan. No, now we need to solve this problem and address it. There are 3 ways how we can address these problems. Either mitigation. We have to mitigate, means slow down the impact. We can see the carbon emissions. We have to slow down the impact. Second one, we have to adapt Means we have to learn how to live with it. And the last one, which is the climate resilience, which is prepared to recover quickly as much as fast. So that's actually the three ways. Let me, one of the plans which have been discussed anywhere, which is called energy transition, okay? Which is the increase of renewables in our electricity supply, okay? And that's the target. The target, if we want to reach up to 90% of renewables. And there are many countries have already reached to 90%. I give you an example. In Australia, we have reached to 90% of renewables in our electricity supply. But there are many other countries which need to work on it. So it's expensive. In order for us, we need to reduce the amount of the traditional fossil fuel in our electricity supply system. So that's the plan. Let me tell you this. This is my start of this is all the introductions. Now we talk about this. This is a very important slide. It shows the load and the source. Okay? What we have here. If you look into here, what you can see, I don't know the pointer is working or not. It does not work. So what you can see on the right-hand side, you can see all the load, different types of loads. We have, for example, we have appliances, TVs, lights, motors, automation, industry, power supplies, and so on. These are loads. Okay, on the other side here is the sources, where you can see the different types of sources. You can see the different types of sources here, and they can be from storage, can be from wind, from solar, from different types. What's the main common part here? The common is this block, here. You can see this block here? These blocks, the blue blocks here, dark blue. These are dark blocks. These are, what is this? These are all power electronics. Now, when you go and go to the shop and buy an air conditioning, what they tell you? They tell you this is a conventional air conditioning, this is an inverter-based air conditioning. When you go and buy fridge, they will tell you this is a normal fridge, this is an inverter-based. You go and buy washing machine. This is a washing machine normal. This is an inverter base. You go and buy lights. This is an LED. This is a normal. What's the difference of this? What is inverter base? It means the power electronics. So all the appliances that we use today are all power electronics driven. Every appliance, just name it, any device that you have, it has a power electronics in it. Why? Because power electronics helps to reduce the energy consumption. So that's why we use the inverter inside the air conditioning system, because we want to reduce the energy consumption. We want to use it in the washing machine because we want to reduce the energy consumption, right? So that's the idea. So from all the loads, 99% it's power electronics driven. We're talking about electric vehicles now. We're talking about electric aircraft. So electrifications can only happen through power electronics. Okay, so that's from the load side. If you look into the source side, the other side, this side, the left-hand side, what you can see also, photovoltaic. Photovoltaic, we never work without inverters, right? Wind, we never work without power electronics. Electric vehicles. Storage, we never work without power electronics. So what you can see, there is a dominance of power electronics on the source side and also on the load side. So, and I will give you some examples, how we can make this impact. So I'm going to explain how power electronics can help reduce the energy that we consume and also we use. Let me give you this. This is the power supply. This is actually a laptop power supply. I don't know, all of us have this, right? So usually we have AC, we have around between 9 volt to 19 volt DC, and then it goes to the laptop. In the laptop, there is the converters and the voltage regulators. This is for the display, this is for the disk drive, this is for different memory, so different voltage levels required inside the laptop. You understand? This is clear, right? So from the AC, we generate this, and we have this. Different requirements of voltage. I'm going to give you an example how this is the circuit diagram of the power electronics, you know. This is the circuit diagram that we use in this power supplies. Very simple one. Very simple circuit, you know. We have between around 400, between 240 volts, and then we convert to generate the DC. So what changes? And this one used to be hard switching. Hard switching. So what actually we did 20 years back, you know. So we moved from hard switching to soft switching. Just this change. We add these capacitors and these inductors to create the resonance and switch at low, zero voltage, zero current switching, and increase the frequency from 50 kilohertz to megahertz level. So we can reduce the size of the capacitors and the inductors. Let me show you the impact. It was the maximum efficiency of the hard switching power supplies was around 85%. Maximum efficiency. So what that means? 15% losses. 15%. I know the power of this is around 70 watts. Let's assume it 100 watts. So for every 100 watt, we lost 15 watts. Is that a lot? 15 watts. Not much, right? But multiply by how many laptops we have around the world? Billions? 15 multiplied by 1 billion. You can see the amount of saving that you can do. So you cannot look at your scale level. You have to look globally. So let's see. Let me give you we did some statistics. So it improved 2009, improved around 90%, 2010, 2011, 2012, and we reached around 95% efficiency. Just changing from hard switching to soft switching. Very small capacitors and small inductors. So this is the amount of saving. So how much is the amount of saving? The amount of saving, it's more than 20% improvement in the over 8 years. And what is the amount of electricity? The amount of electricity we save by this improvement is equivalent to what is generated by 60 nuclear power plants. 60 nuclear power plants. One nuclear power plant can generate, usually nuclear power plants are between 900 megawatt to 1 gigawatt size. Nuclear power plant, usually around 1 gigawatt. One nuclear power plant will able to generate around 7 trillion watt-hour of electricity per year. 7 trillion watt-hour of electricity. 7 times 60. So this is the amount of saving of electricity when we introduce the soft switching in these laptop chargers. So you save 60 times 7 trillion watt-hour of electricity. So you can draw how much carbons we have saved. Because this 7 times 60 trillion watt-hours have to be generated from coal or gas or petrol. You see the amount of saving. And you can see the impact of power electronics. Small change. Just changing the circuit topology from a hard switching to soft switching. Before we switch at any voltage, any current. Now we switch at 0 voltage, 0 current. That's the losses. And you can see the impact. So, and as I say always, you look into the global perspective. Don't look at yourself. Don't look, 15 watt. What is 15 watt? This is nothing. Maybe in Algeria, maybe in 1 year it costs you maybe 1,000 franc or 2,000 franc. But when you look at it globally, then you can see the impact of emissions. So this is one example, very small, simple example. I'll give you another example. This is applied also for all data centers and things. So let me give you an example. This is data centers. You know, data centers are becoming very, very important. You know, data centers, you know, like Google, Tencent, Microsoft, X, Facebooks, they have large data centers, banks, online transactions. So they need to have a power supply 100%, not 99.9. The power supply have to be supplied 100%, all the time, whatever happens, because imagine, what do you call, Google goes for 1 minute off, or less than 1 minute, 30 seconds. You know how many billions of they will lose? Billions of dollars. You know, like Amazon, you know, all these big companies, they invest a lot of money in data centers, you know, and storage. So they will have what they call the UPS system. And this UPS system for these data centers, and it's mentioned somewhere here, yeah, data centers will consume 10% of the electricity generated by 2025. So the amount of electricity that will be consumed by these data centers will increase because, you know, the cloud, you know, you see clouds, these are all data centers, you know. So the consumption of electricity will significantly increase. And this is the architecture of the existing data centers. What we have the grid, and then we have UPS systems, which is conversion from AC to DC, DC to AC, and then storage. And then we will have the servers where we have the voltage regulators that supplies the required voltage. Can you see these green boxes? These green boxes are conversion, right? Every time when we do conversions, we have losses. There is no 100% efficient conversion system. So far, it does not exist. You can achieve 99% maybe, but there is always losses. So you can imagine 1, 2, 3, 4, 5, 6, 7. There are 7 conversion stages. Assume, in the best case scenario, each stage there is around 3% to 5% losses. So you're talking about how much? 30% losses in the system. So what happened? Starting from this year, 2023, Google already have moved from this architecture to what we call DC data centers. Why you have to do conversions? So what you do here, instead of doing this, so you have one converter which is AC to DC, and then storage, and then goes to all DC. Because inside the server, it's all DC. Why you have to use AC? So we remove, how many stages we remove? We remove few stages of conversion stages, one here, one there, you know, so it's almost the saving, it's around 5% amount of saving. Just removing 2 conversion stages. And this is equivalent to what's generated by almost 15 nuclear power plants worldwide. So moving from AC to DC data centers can save us a lot. How about if we change this grid with the PV? If we change it with the PV, we don't need the AC to DC anymore. We can supply directly to the batteries and then supply to the UPS system. So, and 5% only, I'm talking about 5%, maybe less than 5%. And you can see the amount of saving that we can do. The other example, which also power electronics plays a major role, is lights. And you can see how many lights here, you know. It's a lot of lights. And if we use more efficient light bulbs or more efficient devices, see the amount of saving, you know, if we move from this bulb to the saving, we can save around 20%, 20 times energy efficiency. And you can see the amount of saving. It is estimated to be around 450 nuclear power plants. I know switching to LEDs is not cheap, it's expensive, but if we do it gradually. For example, you have this lecture hall, no, I think it's all LEDs, I hope so. Doesn't look like, but, so if we use LEDs, that's the amount of saving. And LEDs what? It's a normal, LED needs an LED driver. LED driver is a power electronics. You can see the impact that power electronics can help in saving the electricity. The other big what I call big brother, which is the motor drive. 60% of electricity generated, actually, it comes from, or it's used in motor drives in industry. Or most of the electricity, especially industrial, I'm talking about industrial countries. In Algeria, maybe it's a bit different, but if you look into United States, 60% of electricity generated is used in industry. The other 40% is used in domestic, transportation, commercial. 60% goes to industries. In China, the same. In Europe, this is the same. So there is a big electricity consumption in the industrial sector. So if we use what you call VSDs and VFDs, variable speed drive, okay, and this variable speed drive also, it's used to try to reduce the energy consumption in electric motors. We can save around 30%. I'm talking about motors which does not operate at full load, because if the motor operates at full load, we don't need the VSD and VFD. But if the motor, the load is changing, so VFDs and VSDs are important to energy saving. So, 300 nuclear power plants. And this VSD is what? It's a rectifier and inverter. You have a fixed, what I call voltage fixed frequency. You put it inside the VFD, you generate a variable voltage, variable frequency. It's a power electronics. So there is a lot, what I call saving in this, what I call motor drives. Okay, so this is some examples that you can see the impact of power electronics in trying to reduce or use the electricity more efficiently, is to try to be innovative. And I think in the last 20 years, power electronics has been a dominant component in our appliances and our loads. Also in terms of renewables, I'm talking about renewables also. In renewables, you can see there is a tremendous increase in terms of renewables, in terms of solar, wind, and all other appliances. I'm going to go through fast this one. I would like to mention here, you can see, for example, the use of renewables is increasing and the use of non-renewables is decreasing. So that's a good sign. We hope one day we will reach to the zero non-renewables. If you look into the wind and the wind energy, you can see wind energy, we reach almost 900 gigawatts. But the good things about it, one single wind turbine can able to generate around 50 megawatts. And it's 100% power electronics driven. What does this mean? It means now we have reached to a stage where power electronics devices are able to handle high power. 15 megawatts, single wind turbine. What does it mean? It means the components, especially with the introduction of the silicon carbide and the GaN devices, actually enable us to operate at very high frequency, very high current, and very high voltage. So this is the main breakthrough. You can look into in the 90s, the use of power electronics is zero. We moved to 100%. And this is the development in the semiconductor technology. It means the semiconductor devices are becoming what you call very able to handle. And also the control. We have very high processing powers and very sophisticated power. So in terms of wind, it's all power electronics driven. The same thing goes for photovoltaics. I think photovoltaics is increasing year after year. And if you look into the photovoltaic systems, it's the same. We have the renewables, and then the interface, it's always power electronics. You need the power electronics to generate the PV. Wind, I think I have mentioned just now. I'm not going to go in details unless if someone has specific questions. I know you come from different backgrounds. I try to keep the presentation as general as possible. But if you have specific questions on specific topics, I will be more than happy to address it. So in terms of wind, there are different types of configurations that we use. You can see either it is partial scale converters or full scale converter. You can see the second diagrams. 15 megawatts goes through this AC to DC and DC to AC converters. And this is a major breakthrough actually in the design. Yeah, there are different types of topologies that we use, either low voltage or high voltage topologies. I will try to move a bit. For the PV, also the same. We have different topologies, okay, from micro inverters to central inverters. We're talking about a few hundred watts here, few hundred watts to megawatts, okay? And each one have pros and cons. If you ask me, for example, which one is the best, it depends what you are looking for. If you're looking for the cost, then the central inverters are the best. In terms of performance, maybe macro inverters will be the best, but they are expensive. So there are different, selection criteria that will be applied in the selections of these devices. Okay. Yeah. In terms of grid connections, we have different types of way on connecting to the grid, either a transformer, low frequency transformer, high frequency transformer, and also even transformerless. But also there are issues that we need to address, such as the leakage current, common mode voltage, and so on and so forth. Yeah. There are a few topologies also. I'm not going to go through this. And the recent one, which is the hydrogen productions, where we see a lot of countries are pushing for hydrogen and green hydrogen productions. It's still not economically feasible because the cost of generating hydrogen is still very expensive. But it has some bright lights at the end of the tunnel. Maybe in the future we will try to minimize. And that will happen similar to what happened to the photovoltaics. Photovoltaics 20, 30 years ago, it was very expensive. In the 1970s, the cost of 1 watt was $75 per watt. $75 per watt. Today, 10 cents per watt. We're talking about the span of 50 years. The costs have reduced from $75 per watt to 10 cents. And that's what happens in every technology, because the technology will be matured. There are a lot of investments. There is a lot of new technologies. And the same thing goes, we will go for the hydrogen. But hydrogen has potential, in the future to be one of the solutions. But it's still very, very expensive. But I'm talking about power electronics. In hydrogen productions, we need to power the electrolyzer to generate hydrogen. So we need the power electronics. And there are many, the existing topologies which using either the SCRs, rectifiers, different 12, SCRs in controlling the hydrogen productions, but they have problems with very bulky because of transformers, large transformers. We use a large three-phase transformers. So we try to look into what will be the best solution to eliminate all these transformers. Because very huge transformers, and also they generate a lot of harmonics because we're using the SCRs. Then move to using the IGBTs and MOSFETs. That improves a bit the power quality, but still the transformers, big issue. And the most recent one is using the MMCs, multi-modular converters. And here we managed to eliminate 100% the transformers. So we do need the low frequency transformers, which are very bulky. And this is the trend now, which is modularity, scalability, and fault tolerance. Because through these MMCs, we will have modularity. Means modularity is a module level. One module fail, and plug and play. One module, for example, it's faulty, the system still works. Maybe at reduced power, but still continues to work. So it's modularity, scalability, and fault tolerance. Scale means I have 5 megawatts, I want to make it 10 megawatts. Very easy. Cost is cheap because you fabricate the same modules. Okay, so that's modularity, scalability, and fault tolerance. Professor Krim, you have to tell me the time. Yeah, because, we lecturers, we make money by talking. So if he doesn't stop me, I will continue talking till tomorrow, You just tell me the time. Yeah, please. So this is the trend. So we can see from here, we managed to eliminate the transformers, the low frequency transformers. So that's actually, and improve the performance of this. So maybe the last few slides, I would like to share with my colleagues and some of the students the outlook. What is the new area of research focus now? Because we need to, when we do research, we don't do research of the current problems. We do research for the next 20 years problems. We don't address the current issues. You know, the current issues already have solutions and maybe people. But as a researchers, we always look into 20, 30 years back, It's coming, you know, the future. And that's very, very important to look into this. One of the focus areas in the power electronics is the hybrid inverters will become more popular. Inverters, usually they used to convert AC to DC. That's the first time when we do it. And then able to inject active power. 5 and must be the total harmonic distortion must be less than 5%. That's the requirement. 5 years later, then they will see the requirement is able to active and reactive power. 5 years later, then the quality of the waveforms, able to communicate with other inverters. 5 years later, then maybe the inverter must have an MPPT, maximum power point tracker. 5 years later, inverter must have battery charging because most of renewables will have storage. So the inverter should be also able to act as charge controller. So the future inverters will not be just an inverter. It should be able to do active, reactive, and then the most challenging one is to be able to inject power and control stability of the grid. Because the previous inverters are grid following. Grid following means they follow the grid. Means we assume the grid has stable voltage, stable frequency. And then we use the phase loop, and then as a reference, and then we inject the active and reactive power. But the new inverters, and this is also a very hot topic, which is grid-forming inverters. Means the inverter should be able to help stabilize the frequency and the voltage of the grid. Means you connect to any voltage, any frequency, and help to stabilize the frequency and the grid. Because the grid now, you know, it's becoming less what you call inertia. Means there is no gas power plant, because all of them are inverters or renewables. Who is going to stabilize the grid? There is no large power plants. So everyone is solar, is intermittent, keep changing. So the requirement of new inverters have to be grid forming. And there is a lot of work actually in this topic, you know. The other topic, it's this what we call DC nanogrids. If you look into this slide, you can see the current practice. The current practice, what we will have a grid, PV, wind, storage, electric vehicles, and then in the bottom we have all the appliances. So what we do actually, we generate power from the PV, and then what we have? We have DC-DC converters and then inverters and connect to the grid, right? The same thing goes for the for the wind. The same thing goes for the storage. And then when we want to use it, because most of the appliances are inverter-based, right? So we convert to DC again. So we have conversion on the upper side and the conversion on the lower side. And as I say, if only assume 1% or 2% losses, you just multiply. So the new trend is to move it to what we call DC nanogrids. DC nanogrids means, since the supply is DC, the loads can operate on a DC, why do we need the inverters? We don't need them. You just need to create a DC bus, the DC voltage bus, and then you connect your appliances to it. Because your light is DC, your TV, LED is a DC, your fridge is DC, your washing machine is DC, your cooking, induction cooking is DC. You know, your car is DC. Why do you need AC? So this is the future. The future will be for DC. And I give an example, many countries, you know, for example, I give you an example in Australia. In Australia now, new house It's in the, what do you call it, the guidelines for building the house, the kite charge. And it's required, no stove with gas, not allowed. You must have induction cooking. Every house must have electric vehicle charging. You have a car or you don't have a car, you must install it. So the future is moving into this. So what you can see, even within a house, you can run on a DC without any problems. But this requires a lot of investments, to move from AC to DC requires a lot of investment. But there is a lot of work, research on harmonizing AC and DC to work together. We call it harmonizations. And we have DC nanogrids, AC nanogrids, and then how they can operate together. So this is a new focus area, which actually, it's a good topic, and there are a lot of work on it, The other focus area, which is electric vehicles. And in Algeria or anywhere in the world, I don't know in Algeria what's the plan, but many countries have already put a deadline. For example, in Australia, they say by 2035, there will be no new car. They will not allow any registration of new car, gasoline car. 2035. What does this mean? You can have a car, you can have it for up to another 100 years, but you cannot sell it. You cannot buy a new car, non-electric. So 2035, whenever you want to buy a car, it must be electric vehicle. I think few countries have already announced. I know, may not possible, maybe 100%, maybe they will achieve 60%, at least they have a vision. They have a plan. Everyone puts a plan. If you achieve 40%, 50%, is good. Maybe it will not happen at 2035, it will happen at 2040 or 2050. But it will happen. And you can see the houses starting from 2024. Every house built new must have charging station. You have a car or you don't have a car, you have to have it. It's a requirement. And this is a very hot topic, actually. And in electric cars, electric vehicles, there are lots of research focus areas. One, for example, is the optimum. I know the infrastructure need to be built, but for example, what is the location of the charging stations? Where we put them? Do we put them in the city, on the highway, in the shopping malls? So there is a lot of research on the optimum location of charging stations. And this can be done, Another topic, which is fast charging. Fast charging means the electric vehicles currently can go up to maybe around half an hour. You reach 80% charging. So there is a lot of focus on how to design fast charging, what we call electric vehicles. Means within 10 minutes, you can charge their electric vehicles. Fast charging. DC versus AC charging. There's a lot of work. The impact of charging on the grid. Because imagine you have hundreds of cars, or thousands of cars connected to the grid, withdrawing a high current, high voltage. What will happen to the grid? It will collapse. The grid will collapse. So you need to define a mechanism how we are going to charge. Maybe some cars are charging, some are discharging. Yeah, because that's why, and the electric vehicles will play a major role becoming what you call mobile storage. Mobile storage means charge during the day at your office, because, for example, you park your car outside, it's charging station by solar. At night, when you go home, you plug your car to the house. So your car supplies electricity to your home. Because the price of electricity changes, I don't know, in Algeria, I know it's fixed. But in Australia, for example, price of electricity can go from negative to almost $0.30 per kilowatt hour. Negative, what does it mean negative? Means they pay you when you use electricity. Midnight, for example, 1 o'clock, 2 o'clock, 3 o'clock in the morning, no one use. Electricity it's free, not free actually. You make money by using electricity. So how you can charge your car, and discharge, when you charge and discharge. So this is a lot of studies works in. And there is another topic, which is the wireless charging of electric vehicles. I personally have a few projects, around $5 million project on this, on designing wireless charging. Because we believe the future, and as I told you just now, we work on the next 20, 30 years project. Wireless will be the way. Because when you have an electric vehicle, electric vehicles made in Europe, in China, in US, in Japan, in Australia, everywhere. Different standards, different plugs. Do you need to have an adapter everywhere you go? So what we see, the future will be for wireless, means when you park your car, you don't have to do nothing. The power will easily transfer from the coil to that. There are a lot of challenges in it. I think it's already applied in the phones, but I'm talking about 20, 40, 80 kilowatts system. You know, I'm not talking about low power. Low power is already mature technology, but we are now working on high power applications. That's wireless charging. And in wireless, there are two. We're talking about static and dynamic. We're looking in the future where the car moves and is charging. Means, for example, you have كما هنا في الجزائر عندنا الاوتورود من الجزائر مصيف الجزائر عندك تروى لين. One of the lanes is wireless charging. So your battery low, move to the other lane to charge. So like this, we can extend the range of the electric vehicles. Because one of the issues of electric vehicle is the range. People are, I cannot reach to my destination. So the problem of battery. So through wireless, dynamic wireless, and we already have we have developed a system already around the university bus, which charge while is moving. And this is one of the focus area, which is dynamic wireless charging of electric vehicles. And I know maybe some people say it's too far. I don't see this too far. I see it like in next 10 years to 15 years. And if I give you an example of the data, the internet. You know, in 1996, remember when we started internet, 96, 95, 96? When you go and buy laptops, you know, you must use LAN cable, right? LAN cable, the LAN cable to connect to internet. Just show me new laptops have a LAN port today. None. All new laptop does not have a LAN cable. What does it mean? It means the data will transfer wirelessly everywhere. Everywhere. You are here, you are in the office, you are at home, everything become wireless. And the same thing will happen to the power. It's the same, the transitions will happen in the power area. So we will move to wireless. It will have a lot of issues, a lot of problems, but it will be the new future. Energy storage, another focus area which is a lot of work actually is going on the energy storage because, as I say, we're moving from traditional to renewables. Renewables will never work without storage because the intermittent nature. We need to store the energy. Wind or solar need to be stored. So there is a lot of work on the storage devices. The device itself means the types of batteries, the types of maybe hydrogen, maybe different types of storage technologies. So this is people from materials, people from chemistry. I think it's very important to look into these areas. And let me show you this, maybe one of the last slides. This shows the trend of the electric vehicles. It's expected to reach around 100 million cars by 2030 or 2035. Electric vehicles. You know, the estimation of the current we call fleet of electric vehicles will reach around 100 million cars. That's very good. But the issue is what we're going to do with the batteries inside these cars. You know, you have 100 million car. Every car, how many kilowatt hours of batteries it has? because the life battery of these cars will run between 10 to 15 years. What are we going to do with all these batteries? Are we going to throw it inside the environment so it causes a lot of problems? What are we going to do? So this is a new focus area, which we call them second life batteries. These batteries need to go another life. We call them second life. Because in order for us to reduce the environmental impact, we need to extend the lifespan of these batteries as much as possible. So what will be the potential application? Stationary application, renewables. Because most of the batteries will retire when they reach 80% of the initial charge in the cars. When they reach around 80% of their charge, state charge, they will be replaced. 80% is a good, still can be used in renewables. But there should be a research done, because these batteries made from different manufacturers, different technologies, different state of health. So we need to do sorting, we need to test them, and then put them together, and then storage them. And this already started, you know. We have, in Australia, all houses have renewables, have solar. But the problem in solar in Australia, when you buy electricity from the grid, is around 25 cents per kilowatt hour when you buy. When you sell from the solar, 5 cents. Cheaper, you know. You understand the technology, because it's an investment. Everyone has solar. So when you want to sell, it's 5 cents. When you want to buy, 25 cents, 5 times. Yeah, because market is free, you can change. You don't want to connect to grid, you have different suppliers, you can switch. Today I am on this, tomorrow I will switch, depends on the price. So what we are going now, we have what we call neighborhood storage. Small, around 15 houses, we will have this container. We have second life batteries, we store energy, so we don't sell to the grid. We store all the neighborhood, we store the energy, and at night we use from the storage. So neighborhood storage, and all using second life batteries recycled from the electric vehicles. So this is another area, and in the batteries there are many issues that need to be addressed, especially the BMS, the battery management system, and there are many issues because they are second life, means you expect to have a lot of problems. And one of the suggestions we have made to the car manufacturers, all the new cars, the EV cars, the new ones, need to have data logger, memory card with the battery system to store the data of charging and discharging. So when we recover these batteries, we have this memory card, we read the data, we know how the battery gone through for the last 10 years. So we can combine it with another correct battery. So this is another very hot topic, especially on the protection, the performance optimizations, and also the calculations. And there are also few ways on how we combine this. We call second life batteries, different approach. Either we use single central inverters, or we use what we call the modular, or we use the power electronics devices where we have some sort like an MMC. If you look at it here, it looks like an MMC, it looks similar to the MMC. We have different battery cells, and then you are connected to the full bridge. I think that's my last slide. So in conclusion, the reduction of emissions, like we have seen before, and I've given you some examples how power electronics can help achieve neutral carbon society. We see that from the skill level, from small skill level, may not be visible, but if you put it at a global perspective, you can see the impact as engineers. And I know many of you, maybe they are chemists, people are maybe in different areas, they can have their own contribution. So I'm making publicity to my discipline, power electronics, but I think every one of us has a role to play and has different one. Even the people from literature, people from arts, when we build the neighborhood batteries, what we do, a container, doesn't look nice. So what we call artists. We call the artists to come to decorate this container to look nice. And people will come take pictures now, next to the batteries, you know. So every one of us has a role to play. People from forestry, so we ask them what will be the best trees to plant around this neighborhood batteries. So in terms of this kind of research, actually it should be a multidisciplinary, and people will appreciate this. You know, so that's my conclusions, and I will be more than happy to answer any questions you have. Thank you very much. Okay.
Thank you very much, Professor Saad, for your very interesting presentation.